In this video, we will show for a long transmission line how the formulas of sending in voltage, sending in current, receiving in voltage and receiving in current are developed to find voltage regulation, line losses and transmission line efficiency. Now, in a long transmission line, we assume all four parameters are available. So, series resistance, series inductive reactance, shunt conductance and shunt capacitance, all four parameters are available, right? Now, we assume the total length of this long transmission line is L and total series resistance is R, inductive reactance is XL. So what will be the total series impedance? It is Z equal to root over R square plus XL square, right? Also for shunt portion, we assume the total shunt susceptance is B and shunt conductance is G. Therefore, we get total shunt admittance for whole length is Y equal to root over D square plus B square, right? Now, in case of long transmission line, if the total line length L is divided into n section, so this is one section length, this is one section, this is one section until n section, right? So we consider each section has same amount of line parameters. Let's say if there are n section, then for one section series resistance will be R by N. Similarly, for one section inductive reactance will be XL by N. For susceptance we will get B by N for one section, and for conductance we will get G divided by N, right? So by this way all four parameters are distributed in the long transmission line. Now analysis of long transmission line. Let us consider a long transmission line of length L. So Vs is the sending in voltage, Is is the receiving in voltage and IR is the receiving end current, VR is the receiving end voltage, right? Now we consider receiving end at x equal to 0. Therefore, for L length, sending end will be x equal to L, right? Now we consider a small portion of length dx, which is x unit far from the receiving end, right? So here, which is x unit far from receiving end. Now we consider Z is the series impedance per unit length of the transmission line. So for dx portion, series impedance will be Z dx, right? Similarly, Y is the shunt admittance per unit length of the transmission line. Therefore, Y dx will be the shunt admittance of this dx length, right? Also, we consider V plus dV is the voltage at the end of this small portion towards the sending end, right? And V is the voltage at the end of this small section towards the receiving end, right? We consider I plus Di, current is entering into this dx section and I current is leaving from this dx section, right? Now what will be the voltage across this series portion of dx and shunt portion of dx? So we already assume at one end of this dx portion the voltage is V plus dV, right? And at another end the voltage is V. So if V plus dV is the voltage at this end and V is the voltage at this end, then we get dV voltage across this series portion, right? So we write dV equal to, what is the current entering this series portion? I plus di. So we write I plus di. What is the impedance of this series portion? Z dx. From here we get dV equal to Iz dx plus Z dx di. Here dx is very small, di is very small. So we can say the multiplication of Z dx and di, it is very less than Iz dx. Therefore we can ignore Z dx di, right? From here we get dV dx equal to Iz, right? This is equation number 1. Next, what will be the voltage drop across this series portion of dx, right? So the voltage is already given as V. So V equal to IR. What is the current? We can see here the total current entering this series portion is I plus di, and the current leaving from this series portion is I. So rest of the current, which is di, this current is entering this shunt portion, right? This di amount of current basically is the leakage current, which is entering into this shunt portion, right? So we can write V equal to current di. What is the impedance? 1 by y dx, right? From here we get di dx equal to yv, which is equation number 2. So we already had dv dx equal to Iz from equation 1 and di dx equal to yv from equation 2. Now we differentiate equation 1 with respect to x. So what we get? Double derivative of dv dx equal to ddx Iz, right? So we differentiate this equation. From here we can write d square v dx square equal to, we can write di dx is equal to yv, right? From equation 2 we can get di dx equal to yv. So ultimately we get d square v divided by dx square is equal to yvz, right? This is equation number 3. Now the solution of this differential equation of this equation 3 is v equal to k1, which is a constant, hyperbolic cos x root over yz plus k2, which is a constant also, hyperbolic sine x root over yz, right? This is equation number 4. So this is the equation number 4, right? Now we differentiate equation 4 with respect to x. So what we get? dv dx equal to k1 root over yz hyperbolic sine x root over yz plus k2 root over yz hyperbolic cos x root over yz, right? Again from equation 1 already know dv dx equal to Iz, so we can write Iz equal to this right hand side, right? From here now we can get the value of I equal to, just divided this portion by z, so we get root over y divided by z equal to k1 hyperbolic sine x root over yz plus k2 hyperbolic cos x yz. This is equation number 5, right? Now we want to find the value of k1 and k2 constant. So we can get the value of k1 and k2 constant from equation 4 and 5 by applying the receiving end condition. So at receiving end, when x equal to 0, voltage V equal to VR and current I equal to IR. So if we put X equal to 0, V equal to VR and I equal to IR, then what will be the condition of equation 4 and equation 5? So from equation 4 we get V equal to K1 hyperbolic cos X root over YZ plus K2 hyperbolic sin X root over YZ. Now if we put all this condition, then V will be VR, right? Then K1 hyperbolic cos X will be 0, right? Multiplied by root over YZ plus K2 hyperbolic sin X will be 0, right? So from here this portion is 0 and the value of this portion will be K1. Since hyperbolic cos 0 is equal to 1, right? So here we get K1 equal to VR, right? Again from equation 5, if we put all this condition, then I will be IR, right? And this X, this will be 0 and this X, this will be 0, right? So this portion will be removed and in this portion we get K1 since hyperbolic cos 0 is equal to 1, right? So we can write IR equal to root over Y divided by Z multiplied by K2. From here we get K2 equal to root over Z divided by Y multiplied by IR, right? Now in equation 4 and 5 we substitute the value of K1 equal to VR and K2 equal to root over Z divided by Y IR. So after replacing we get VR here. So before it was K1 here. So now we replace by VR, right? Similarly this portion was K2. We replace by root over Z divided by Y IR, right? So this is equation number 6. Similarly for current, it was K1, so we replace by VR, and it was K2, we replace by root over Z divided by Y IR, right? So this is equation number 7. Now sending in voltage Vs and sending in current Is are obtained by putting X equal to L in equation 6 and 7. So at X equal to L, here V equal to Vs, right? And current I equal to Is, right? So in equation 6, we put X equal to L. So before it was X, now here we put L. Similarly, it was V, so we put Vs, right? Before it was X, now we put L, right? And for current I will be Is, right? And here it was X, now we put L, and here it was X, we put L, right? So this is equation number 8, this is equation number 9. Now we can write L root over YL equal to Ly multiplied by Lz, right? In this form we can write. So from here we can write Ly, this is Ly, which is the total admittance of the line, as uppercase Y, right? And total impedance of the line, which is ZL, we can replace this by uppercase of Z, right? Again from lowercase root over Y divided by Z, we can write root over YL. We multiplied L numerator and denominator. So from here we can write root over uppercase y divided by uppercase z, right? Now after putting L root over yz equal to root over capital Y z and root over y divided by z equal to root over capital Y divided by capital Z, then equation 8 and 9 become these two equations, right? So here Vs equal to Vr hyperbolic cos yz plus Ir root over z divided by y hyperbolic sine root over yz. Similarly, Is becomes Is equal to Vr root over y divided by z hyperbolic sine root over yz plus Ir hyperbolic cos root over yz, right? Now we can find the value of hyperbolic sine and cosine through expanding in terms of their power series. So we can write hyperbolic cos root over yz equal to this and hyperbolic sine root over yz equal to this, right? And we get this value following this formula, right? So from here to basic equation we have got. One is the equation for sending in voltage Vs and another is sending in current Is. Now here is a problem on long transmission line. A three-phase transmission line of 200 km long has the following constant. So resistance is given as 0.16 ohm. Reactance is also given as 0.25 ohm. Shunt admittance is given, so value of Y is given. So series resistance means this is value R, reactance value is XL, right? Shunt admittance is Y. What we have to calculate? We have to calculate the sending end voltage Vs and sending in current Is when the line is delivering load power 20 megawatt. So PR is given, receiving in power at 0.8 power factor lagging, so cos phi is given, right? The receiving end voltage is kept constant at 110 kV, so VR is also given. So we know the equation to determine sending in voltage, right? So this is the equation to determine sending in voltage. So here VR is given, hyperbolic cos root over yz, y is given, z is given, right? I is not given, but we can determine I since PR is given. So we know PR is equal to root 3 VR IR cos theta. So we can easily determine IR using that equation, right? So basically all the parameters values are given. We just put the values in this equation and we can easily determine the value of sending in voltage Vs, right? So we determine hyperbolic cos root over yz through this series, right? So we know z, we know y, so we can easily determine the value of cos root over yz, right? And we get 0.992 at an angle of 0.26 degree, right? Similarly, we can determine the value of sinh root over yz and we get the value 0.1325 at an angle of around 75 degree, right? So we get cos root over yz and sinh root over yz. So we can easily determine the Vs if we know IR, right? So now we determine the value of IR, PR, which is given as 20 megawatt, VR, which is given as 110, right? So we can easily determine IR and we get 131 ampere. So after putting all the values, we can easily determine the sending in voltage and we get 67366 at an angle of 5 degree this volt. So this is the voltage of sending in voltage, sending in phase voltage. So we can easily get the sending in line to line voltage by multiplying this Vs by root 3 and finally we get 116.67 kilovolt, right? Similarly, for calculating sending in current Is, all parameters values we already determined. So just putting that values and we get 131.1 at an angle of 8 degree ampere, right? And the value will be 131.1 amp, just neglecting the angle from here, right?